All right, after L for linear, I is what you might expect.
Independent.
Independent. I don't think there's anything new about finding independence. If a sample is taken, you're going to do the 10% rule, and if there's not a sample, you just reason it through. Like with the helicopters, they dropped how many? 70? Do you recall? They dropped a lot. 50, 60, 70, I can't recall. All right, they dropped 50 helicopters in a problem we just read, okay? They were paper helicopters from different heights. And it turned out that that was not a sample. That was like an experiment. So it makes sense that one drop was independent of the next. If you used a different helicopter, you can't drop the same one, because if you drop the first one, maybe it somehow altered it so that the second time it dropped better or worse. So you just have to reason through whether the events are independent, but one helicopter drop should not affect the next. So, all right, then N, guess what that stands for?
Sample size.
What?
Yeah.
Sample size, number.
No, it's not. Normal. All right, but what's normal? I mean, we don't expect the line to have a normal shape. We expect it to be straight. So this is where it gets a little tricky. We want the residuals to be normal. In other words, we want most of, if this is a good line and it fits the data well and represents the whole population, we expect the differences, the residuals, to be in a normal shape. Because some of them are going to be far away from the line, but not many. And some are going to be close to the line, most of them. So therefore, the normal is the residuals. So I have to teach you again how to find residuals and do a histogram of them.
Isn't it just like there's no pattern?
Yeah, and
So
that's
what?
another
So
one. Which kind of chart was that? That was this. That was for this. So we can look at the scatter plot, and we can also look at the residuals for lines. The residual is scattered. You guys are remembering all kinds of things.
I am starting to regret using my skip one.
All right. So checking for L, you can look at the residual plot. If it's scattered, that means you have a straight line. And here, for normal, we're looking for residuals to have a normal shape. All right, so now E is equal variance. That's a new one.
There's so many conditions.
Equal variance is also looking at the residual plot. And for each X, you want the dots to be the same distance above as below the zero line. Until I do one, that's not going to make a lot of sense. So it's not too bad to check that. Once you get that residual plot and R,
Random.
right, and that's usually stated. There's not much we can do about that one. All right, so I just wanted a tiny little bit of theory. I'd like to end on the note of doing this for one, and if that's all we get through, I'd be happy. So I'm not sure I'll get to present to you the test statistic or the confidence interval, but we're good to go if we get through liner for our first example. All right, so let us go ahead and finish with theory. You can turn over now. Well, wait a minute. Before you turn over, could you just look at this and see if it makes sense? And then I have it for you partially sketched on the back. All right, I need room. So
You can
I'm
erase
going
all
to get
that.
rid of this older stuff.
Swivel.
All right. Here is what we're doing. It's kind of hard to visualize, and that's why I asked you to look at the board and then turn over, because I kind of have a sketch started for you. So here is what we normally look at, an x-axis and a y-axis, and it's sitting up at the plane of this board, but I'm going to throw it down on the floor. So I'm going to take this and throw it down on the floor. So perspective, we're drawing, it would look like that. Does that look like something sitting on the floor?
Yeah.
Alright, so here's x1. It's going to say be the first value. So here we go, I slant it like this. And here's x2. Maybe slant it like this. Now does it look more like it's on the floor? Or less?
It looks like hardwood flooring.
Alright, it's supposed to look like you're looking at the floor from our perspective. This is a plane that's cutting the board. So it's hard to draw, but... Alright, so, for every value for x, such as the weight of one person, there's all these values for y that are possible depending on the samples. So remember, this sample had this value for y for this x. This was x and this was y, but we're doing a lot of samples. We're doing thousands of samples. So the y is going to change. And the y's should have a normal distribution for this x. So that's my value. For these are the y values, and that's the x value. So I'm going to take the mean of the y value and call it mean of x1 and plot it. So that's the mean of, it's the mean of x1, but it's the y value. So how do I want to say that? I don't know. I won't say anything. I'll just put a dot there. Alright, so that's the mean of the y values, but some of their samples provided y values that were way high, some way low, but most of them were right here. For x2, the same thing happens. Alright, so you can turn over your paper now. You see what I'm doing. And I'm not sure what I drew. Can you show me? What did I put? Turn the paper over. Alright, so I did put a little bit on there. I gave you x1, x2, and x3. I gave you these. So if you would take from the highest point on the x1y curve and drop a dot down to the graph here, and that's what, I didn't do that for you, did I?
No.
Okay, so put that in. And can you show MK?
Mm-hmm.
Alright. So now I'm also going to do that for this one. And then I'm going to put in my third one and drop that down. So, does it make sense to you that the whole curve, the whole, this thing, what am I trying to say? The whole line that represents the whole population, not that, this, is going to be including these lines. So I'm going to draw a straight line that connects. It should be more slanted than that, so imagine that has a slope. So yours are going to have a slope. So connect those, and will it have a slope more than straight? Or does it look pretty straight? Oh yeah, that's better. My board didn't turn out so well. Alright, let me see what that looks like. Yeah, do you see how hers had some slope to it? Right there. So connecting those dots is a good idea. And that is the true line. So you can put in this name on that line, y equals alpha plus beta x. Is that going to help you do any of the problems? It isn't, but I'm just trying to have you visualize what we're trying to do here.
Does Powell do the lines from the medians and the normal curves? Do they go straight down?
Yeah.
Like,
Yeah.
to our
I know what
perspective?
you're
Yeah,
saying.
from here. So that's probably why mine messed up. I should have went like this, and then it would have had a better result. It's my art failing here.
No, like they.
So I should have had,
And they go straight down and
and then it would go more like, whoops.
No? They what?
All right, well,
They go like-
do it like MM. We should already
I just went
get.
straight down, Brian.
It should look
for the
like
most
that.
part.
Okay.
All right, you want to show?
I
show
showed
it?
her mine.
Okay,
Wait, I'll
is
show
yours
you mine.
slanted as well?
Yeah.
All right, so
It's
X.
turned. Look at that turn.
This, I often see, instead of y equals alpha plus beta x, they do not call this y, so you can write another name over it. They call it the mean of y. So I can see why they do that, because they're connecting the means. But It's a technicality in theory only. It may interest you. I'm not sure that it comes up, but it interested me, so I'll say it. The standard deviation is the same on every one of these. So if you find that of interest, you can join my little club. All right, again, is that gonna help you? Is that picture gonna help you do the work?
No.
It is not. So if the theory is confusing to you, read that section of the book. I think they might be able to present it a little better. And we'll go on with the how-to now. All right, so it probably doesn't surprise you that alpha and A are related. So A is an unbiased estimator of alpha. And A, again, is the y-intercept from our sample. So if we get a sample, we're going to use that as alpha. It may not surprise you. B is an unbiased, let me put the word estimator, unbiased estimator of alpha, and B is an unbiased estimator.
What does it mean to be biased again?
It means if you take every single sample that is possible and you put them all on a normal, it'll present a normal curve, and the mean will exactly match the parameter of the population.
Okay.
B is an unbiased estimator of beta. So now this is where you're going to use this information. Not that you won't use this, but that is more theoretical. This is more practical. We're going to take a sample, we're going to find the y-intercept and the slope, and that's going to be our estimator of the true alpha and beta of the whole population. Sort of like we used to do with means. You know, how we used to do x bar was the estimator of mu. Come on, brain, you can do this. Okay, already? Okay.
Yeah, I don't know what.
Down we go again.
Bye.